All right, well, welcome to the last week of vector calculus. Yay, we've made it. 1 week to go. We have two more theorems we got to hit up. Today we're going to talk about Stokes' theorem. Tomorrow or Wednesday we're going to talk about the divergence theorem. But before we get to Stokes' theorem, let me turn it over to you guys in terms of homeworks. So what homework questions can I help you guys with today? All right, so Victor just put in the chat box he'd like to look at number 13 from 6.6. Any others? Okay, well, hearing none, then let me go ahead and get the switch the screen here. And we'll go take a look at that. My computer has decided it's also the end of the quarter. It's dragging. How are you guys holding up? Are you making it? You got 1 week left. Are you going to be able to?
I'm slowly losing
through?
it. I'm not gonna lie.
Yeah.
Because it's so close to the end, though. That's why.
How's it compared to last spring? Because I know that a lot of us had trouble in the spring.
Oh, it's exponentially better.
Yeah.
Oh yeah.
I found that too. A lot of my friends who are not teachers, were asking me how it's going and everything, and I said, like way better than spring, and I think it's twofold. One, we were prepared for it. It wasn't like it was just thrown onto us, because you may remember back in the spring it was like, oh, by the way, next week you're doing this, right? So we had time to prepare, but also we're used to it. We've already gone through a couple months of this style of college, so I think that helped a lot there. But
Yeah, I definitely agree with that. The fact that we were prepared helped a lot.
yeah. All right. Oops. All right. So here we go. Here's number 16. No, 13. Sorry. All right. So we want to calculate f dot ds, where f is given by this field, and then s is the surface of the solid bounded by the cylinder, y squared plus z squared equals 16, and the planes x equal 1 and or minus 1 and x equals 3. Okay, so let's just start here. What are we actually calculating when we do this integral of f dotted with ds?
The area. I don't know. I guess it would be the flux, right?
Okay, so area would be if we were just integrating 1 with respect to ds. But this one, yeah, this is a vector integral. And so f dotted with ds, this is the flux over these surfaces. So basically what we're going to find out is what is the flow through this cylinder, right? Because we got a cylinder capped on the sides, and then we're seeing what kind of flux we're getting. So this is just a measure of flux. Okay, but it is a surface integral. So how do we go about doing that? What do we have to do? I have to write down this problem, so when I go to the whiteboard, I can do it. But what's the process? What do we need to try to do here? Okay, so Victor says we need to parameterize So it definitely helps if we can parameterize the surfaces, right? Because if it's parameterized, then we obviously we change f according to that parameter, but then the integral, we end up doing an f dotted with ru cross rv. So we can get the partials with respect to u and v, cross them. In essence, what we're doing is we're getting a normal vector, right? And then, excuse me, that normal vector is dotted with f. So we're basically getting the portion of the field that's going orthogonal to the surface. All right, so we're going to need to parameterize. What kind of sucks about this one is we have 3 surfaces. Do you see that? I mean, it does say that just S is the surface of the solid.
Yeah, it's the 2 planes and then the cylinder.
Yeah, so think about that, your can of green beans or something, right? You've got the outside, you got the top, and you got the bottom. And for those, we have to do each one of those individually here. So this is really a 3 integral surface integral. It's kind of like, think about that one on the exam that was a line integral that we had to break into 2 pieces. It's the same kind of deal here, right? So you've seen that with line integrals where we've had to break it into different integrals for each of the different curve sections. Well, same idea here. We've got our surface, but now we have to break it into the 3 individual surfaces. All right. Well, let's see if we can do that. So let me go to the whiteboard. So here's our picture. I'll even try to make, no, I was going to do a regular old looking cylinder. Right? So we really have 3 that we've got to worry about. The one is the top. The second one is the bottom. And the third one is the side. All right, so let's parameterize each of these guys. So for surface number 1, this was, I think it said x equals 3. Yeah, it's x equals 3. All right, so can you parameterize that for me?
Three zero.
Okay, so it's going to have 3 for the x. But we don't want 0 here, actually, because the y's do vary, right? As do the z's. So I'm going to go ahead and just do 3 comma u comma v. The y's and the z's are going to vary around, but this would be the plane x equals 3. And for us, the u and the v, these are going to be where the u and the v fit within that circle, right? There is some bounds on the u and v. And so let me just put here the u and v are in the circle. What was it? U squared plus v squared equals 16. All right, so there's the parameterization for the top. The parameterization for the bottom is just about as easy. In fact, when I say just about, it literally is as easy. What's this one going to look like?
Wouldn't it be the exact same except -1?
Yep. Now the x's are -1, but the Y's and z's are still u and v, and they're still in that circle. So those are pretty fast and pretty easy. While we're here, let's go ahead and get RU and RV so we can cross them. So here RU is going to be 0, 1, 0. RV is going to be 0, 0, 1. So if we cross that guy, we get 1, 0, 0. And that should surprise exactly none of you. Because think about what that vector is looking like. It's pointing just in the positive x direction. If we come back to our can, I know I've got things kind of turned sideways, but if this is x equals 3 and this is x equals -1, which way is positive x?
Vertical.
It's vertical and it's upward. So we're getting that that's the normal vector to that surface. I don't know if you can see my shocked face from where you are, but okay, no, that totally makes sense. So what should we expect to see for the other one, for surface 2? The answer should be exactly the same thing, right? Because RU, because this surface now is, again, parallel to x equals 3, so it should go up and down. Well, RU is going to be 0, 1, 0. RV is 1, 0, 0. Or whoops, getting ahead of myself. RV is 0, 0, 1. So again, RU cross RV is 1, 0, 0. Okay, however, we're not going to use 1, 0, 0. Excuse me. What vector are we going to need to use? We're actually going to use -1, 0, 0. Because -1, 0, 0, that one's now pointing down. Why do I need that normal vector to be pointing down? So Victor, when you say negative, I don't know if you mean because x equals -1. It does have to do with flux. I need to have all of my normal vectors either pointing inward or all pointing outward. I need to be consistent. In general, we use outwardly pointing normal vectors. But I need to be consistent because otherwise the signs won't tell me what's going on. Right? Like if that one on the bottom was pointing upward, a positive would mean stuff is flowing in, where on the top, a positive means it's flowing out, and I can't have that. Positive's got to mean either going out or coming in. So for that one, we're going to change that to -1, 0, 0. All right, so while we're here, before we go to this side, let's go ahead and calculate the flux for both of these. Okay, do the flux for both of these surfaces. So let's again start with the top. So let me just remind you, because I've subsequently moved it away. The F was 3xy squared x e to the z comma z cubed. So for surface number 1, with that parameterization, the flux is now going to be 9u squared 3e to the v cubed. So I'm putting in 3 for x, u for y, v for z. So the integral then double integral. Okay, when I dot this with 1, 0, 0, I get 9u squared. So I'll just call it 9u squared dA. All right, so now I need to do that over the circle. But since we're doing this over a circle, let's definitely totally go polar. So this is going to be double integral of, well, the u, that was the y. So we can use r cosine or r sine. It doesn't really matter. I'll use r. But we'll have 9r squared cosine squared times r dr d theta. The r's are going to go from 0 to 4. And the thetas are going to go from 0 to 2 pi. So that'll get me my flux over that one. All right, so for surface number 2, this one, the flux vector is going to be minus, or sorry, the field vector is going to be minus 3u squared minus e to the v cubed. Now I'm plugging in minus 1. But now I need to dot that with minus 1, 0, 0. So this one we're going to integrate 3u squared. Okay, well, do the same thing, go to polar. And there's that piece. Okay, so we're 2/3 of the way done. We took care of the top and the bottom surfaces, but they were the easiest ones to parameterize. Now we got to do surface number 3. We need to do the side of the can. But before I do that, any questions on what I've done so far? All right, well, hearing none, let's go ahead and tackle that third side. Okay, so side 3, this is the one that's given by y squared plus z squared equals 16. So for that one, if I want to parameterize that, first of all, notice that the x's can be whatever we want, right? The x's, they're going to range from minus 1 to 3. So for surface number 3, I'm going to let x be u because it's kind of a free choice. Now the other ones I'm on a circle, which makes you think we want to use r cosine and r sine, and I totally do, but I'm not going to put in a r, I'm actually going to put a 4. So are you guys good with where that 4 came from?
Yeah, for the equation in the cylinder.
Yeah, the cylinder was a circle of radius 4, so the radius doesn't vary. It's just plain old 4. All right, so there you go. There's the parameterization for that guy. So we need RU. It's going to be 1, 0, 0. We need RV, which is 0 minus 4 sine 4 cosine, which makes RU cross RV be 0. And now we're going to get minus 4 cosine, and then minus 4 sine. All right. But again, the question is that pointing the right way?
I think so, because it'd be pointing outward, correct? And the negative y and negative z direction. So it'd be flowing outward.
Okay, so we definitely need it pointing outward. But is this one actually pointing outward? Well, think about this. I know it's kind of hard to picture. So let's look at, we're looking down at the top of the can. Okay, so here's Y and here's Z. So let's think about when we're at 0. So when we're over at this point right here, this is V equals 0 because it's an angle of 0 relative to Y since we chose Y to be the cosine. Let's think about what RU cross RV looks like at that point. We're going to get RU cross RV to be 0, minus 4, 0. All right, so that points solely in the Y direction, but points negative. So that thing's actually pointing towards the interior. We need it to be pointing exterior. All right, so what are we going to do to get one that points outward?
Just change the sign.
Yeah, so we're actually going to use 0 for positive 4 cosine V, positive 4 sine V. All right, so yeah, kind of sucked. But now we're totally good to go. So let's get our field written in terms of this parameterization. So our field's going to be 3xy squared. So 3u times 16 cosine squared, x e to the z, so u e to the 4 sine v, and then z cubed, which will be 64 sine cubed v. But now we need to dot these two together. All right, so all that's gone. So we're left with a 4u cosine v e to the 4 sine v. And then we're going to get minus, is that 256 sine to the 4th v. And so now we need to integrate that thing. I'm going to be lazy.
Why would it be minus 256 sine to the 4th v?
I have no idea why I wrote minus. It shouldn't. All right, so let's put on, say, our du dv. So the u's, those were our x's. They're going to go from -1 to 3. Our v's, those were our angle. They're going to go from 0 to 2 pi. And before you freak out about how terrible this is going to be to integrate, it really isn't that bad. If you look at the u part, the u part's trivial. And then when you look at the v part, probably the part that's scaring you is that first term, but that's actually just a simple substitution. I don't want to call it u sub, but call it w, let's say. You let w equal 4 sine v. Its derivative is 4 cosine v, which is exactly right out front. So that's just going to be a simple e to the w integral. And then the other one, it's trig integrals, but that's what our calculator is for. All right, so you're going to get a number from this. You add it to the number we got from 1 and 2, and that'll get your total flux over that surface. Oof. All right, so what do you think about that one?
I think the video on the homework lied to me.
What the homework say, or the video say?
Well, it didn't do any of that, that's for sure.
What did it do?
Triple integral using partial derivatives.
Hmm. Hmm. Okay. No, that totally works. Because what I was gonna follow up with after I was like, so what do you guys think? I was like, there's got to be a faster way, right? Like it seems like every time we do it, we have something faster. Yeah. So Victor, you just said they use the divergence theorem. Yeah, I haven't shown you the divergence theorem yet, but the divergence theorem is sort of like the 3D form of Green's theorem. Remember how Green's theorem worked? That if we did a line integral around a closed curve, it was the same as doing the double integral of some stuff inside, right? Well, the divergence theorem is similar. Now, if we're doing a surface integral over a closed surface, it's the same as a triple integral of something on the inside. That something happens to be the divergence of the field, which would be where your partials are coming from, Bradley. Uh, yeah, so they basically spoiled it for me.
They
Thanks a,
definitely did.
thanks a lot, my open math.
Because I'm honestly glad Victor asked this question because I didn't know how to do it like this. I couldn't figure it out.
Mhm.
And then the video showed me something completely different.
And it showed you something that we had never talked about.
Yeah.
And so you were probably like, what kind of crazy math magic is this? And rightfully so, right? It sounds magical. Um, all right, you know what we're going to do? I'm going to call an audible. We're going to see how this goes. We're going to skip Stokes' theorem, and we're going to go right into divergence theorem. So I'm going to skip ahead. You don't need Stokes' theorem to do the divergence theorem. But since we're talking this, and since you guys, when you checked the video or whatever, and they started using this magical thing called the divergence theorem, let me go ahead and show that to you. And we'll talk a little bit about how it applies and how we would have used it in this case. All right, so I think I'm going to do that. But up to where we are right now, with what we've talked about, this approach that I just showed you on the whiteboard is the approach. This is how you have to do it. We have to break it into the different surfaces, do each one individually, and then add them up. And it's exactly analogous to when we were doing line integrals. And we had to, like, remember those lovely ones where we were doing like a triangle or whatever? And we had to parameterize each side of that triangle, do the line integral on each, and then add them up. And then we learned later, oh, we've got this awesome theorem called Green's theorem, which basically lets you do that as a double integral. Well, that's kind of the same thing that's going to happen here. All right, so yeah, total audible. We're going to see how this goes. Hopefully, I do better than the Broncos offense did this weekend, but we'll see. Before I go there, though, any questions on how I set this up? What I did for the different pieces. No, we're good. Okay, so let's talk divergence theorem. So give me 1 second here. I'm going to go hop up to my whiteboard. So I will see you guys in just 1 second. All right, so we're kind of to the end of this class. We got a couple more theorems that tie everything up in a nice little bow. And as I just mentioned, we're going to go kind of out of order here. Let's go to the divergence theorem. Now, the divergence theorem is a theorem that involves the divergence of a field, hence the name, right? It's like, yay, mathematician. But basically, this is how the divergence theorem works, right? What it says in terms of the conditions. Okay, so first of all, what we need to have is a piecewise smooth curve. Okay, so smooth curve, hopefully you guys can remember what that means. Piecewise just means as a whole, it doesn't have to be one smooth curve. It's just made up of a whole bunch of smooth curves. So you actually can have sharp turns on this as long as each of the surfaces are smooth. So for example, think of like a cube. A cube we wouldn't consider a smooth curve, but it is piecewise smooth because each of the 6 faces is a smooth curve. Okay. So let S be a piecewise smooth curve that encloses the solid region Q. And I just realized it shouldn't say curve, this should be surface. Okay, so it's a closed surface. Okay, so we couldn't do this with like a elliptic paraboloid, a bowl, unless we put a top on it. We could do it with an ellipsoid because that thing is closed and so on. All right, so it has to enclose a solid region Q. Okay, so we've got this. Then what we know is that if you are integrating f ds, so we're finding the flux over this curve, it's actually the same as the triple integral over the region of the divergence of f. So you remember the divergence, I hope, right? So divergence of f dv. So this is the divergence theorem. Basically, it's a faster way of doing a surface integral of a closed surface. So hopefully you can kind of see the parallel to what Green's theorem was for 2 dimensions. Green's theorem, we had a closed curve. And we saw that it was the same as the double integral of some stuff, right? Well, it's kind of the same idea here. Now we're doing a surface integral over a closed surface, and it's equal to the triple integral over that region of some stuff. And in this case, it's the divergence of f. Okay, so since I'm totally pulling an audible here, I'm not going to prove it to you. We'll save that for later. But let me show you how this works and why this is far superior. So let me go back. I got to grab it because I left it at my desk. Let me grab that homework problem that we were just doing. And let me show you how the divergence theorem is so much faster. So hold on one second. All right, so here was that field from that homework problem. We were given 3xy squared x e to the z, z cubed. And again, the surface, it was y squared plus z squared equals 16. It was that cylinder with a top and bottom of x equals -1 and x equals 3. Okay, so when we are doing it the way that I intended it to be done for this homework, where we are attacking each surface separately, we had 3 integrals to do. One for the top, one for the bottom, and one for the side. Okay, well, check out divergence theorem. So now the divergence theorem, do we have a piecewise smooth curve that's closed?
Yes.
Well, it's clearly closed. And if you look at those 3 surfaces individually, they are all smooth, right? The top and bottom are just planes. And the outside is basically a plane that's been wrapped around. So it's all good. Okay, so what we're going to do is let's actually set this up as a triple integral of the divergence. So let's get the divergence of f. So the divergence of f, I'm going to write it as del dot f, just to remind me it's a dot product of the differential. So we're going to add them up. So I take the derivative of the first one with respect to x, which is 3y squared. I add to it the derivative of the second one with respect to y, which is 0. And then add to that the derivative of the third one with respect to z, which is 3z squared. So by the divergence theorem, we're going to be integrating 3y squared plus 3z squared over the solid region. Okay, so start there, just get the divergence. But now we have to think about how do we describe this region in 3 dimensions?
Cylindrical.
Okay, and we definitely want to use cylindrical. So here's my suggestion for this guy. again, this was our picture. And if we think about, I guess, the way that this is drawn, this is our X. So maybe these are Y and our Z. I'm going to do my X last for my integration, because that's going to be super easy. So we'll have 3y squared plus 3z squared. And just for the sake of something, I'll do dz, dy, dx. So I don't know what these bounds are just yet. But the x I know. Once everything is done, the x's are going to range from -1 to 3. But then in the YZ plane, I'm seeing circles. So I definitely want to go polar. So that's why this is cylindrical, right? It's cylindrical, but turned sideways. So if we go to polar, the 3y squared plus 3z squared, that's just going to be 3r squared. We need an r dr d theta. So then the r's, they're going to bound, those bounds are going to go from 0 to 4. Because again, remember our circle, or our cylinder was y squared plus z squared equals 16. And our thetas, excuse me, are 0 to 2 pi. So by using the divergence theorem, we get one integral to do. It's a triple integral, but that's okay, man. I will gladly trade those surface integrals, which are double integrals, those 3 of them, for one triple integral, especially for one that has such nice bounds, right? This is going to be crazy easy to evaluate. We're going to get r to the 4th over 4, so that's going to be 16 when I plug in 4. 16 times 3 is 48, times 2 pi, so that's 96 pi, times 4. Let's see, 96 times 4, and 3. I had it 376.
384. You were close.
384. So it's 384 pi. So almost to the point where I can do this in my head. I'm going to blame the fact I only slept like 4 hours last night. But it became so much easier by using the divergence theorem. Okay, so the divergence theorem is definitely your friend, but realize it only works when we have a closed surface. So if we had not had a top and bottom, so it was just the cylinder part itself, that one we couldn't use Green's theorem. It wouldn't help us out. Or I say Green's theorem, I meant the divergence theorem. And this just totally reminded me of something else that I need to tell you about the divergence theorem. So this surface, and this is what I get for calling an audible, trip over my feet. When you do the divergence theorem, we need the normal vectors must be pointing outwards. Okay, so we know that surfaces have orientation, right? You can have orientation one way or the other. And in this case, you definitely need to have orientation outward. All right, so let me show you another example. I don't know that I really need to convince you how good this is or how useful it is, but I definitely want to show you another example before we just say, hey, yeah, here it is. Okay. So let's try this.
And just to be clear, that means pointing outward from the surface.
Yes. Because when I talk about the normal vectors, those are the vectors, the normal vectors to the surface. And so like, here's a surface, and I can have either normal vector on this side or on this side, right? And so in order for us to have orientation, just like with a curve, because if I just draw a curve, which way are we going? And it's kind of arbitrary, right? For this one, though, we're going to say that the normal vector that's showing us orientation is pointing out from the enclosed region. Does that answer your question, kind of?
Sure does, yeah.
Okay, cool. All right, so here's another one. Let's say that, let's find the flux of, for this guy, how about we go with x, or so y squared e to the x x minus z. And we're going to go over the unit sphere centered at the origin with outward orientation. All right, so this is another flux integral, and we would want to use a surface integral. So I want you to think about what we would have to do if we didn't use divergence theorem. First of all, notice divergence theorem totally is going to work, because we do have a closed smooth curve, and it is just a curve now, right? It's just the sphere, but it is closed. And we've got our outwardly pointing oriented surface. So everything's good to go. All right, now if we didn't use the divergence theorem though, what would we have to do?
Parameterize our region or
Okay,
our curve.
so we'd have to parameterize the sphere.
Mm-hmm.
That's not terrible. We know how to do that, right? And we actually wouldn't have to split this one up. Victor just put in the chat, split it. Turns out we don't have to split this one up, because we can define the sphere all at once parametrically using spherical coordinates, right? We would let rho equal 1, because it's a unit sphere, the radius is fixed. And we would just let the two angles be our u and our v, whichever way we wanted it set up, right? So if u was, say, theta, then the u's are going to go from 0 to 2 pi, and then v would go from 0 to pi, since that represents our phi, or vice versa. But we could do it in one. So it's not terrible there either. Turns out it just is one double integral, one surface integral. But I don't know if you remember that, yeah, so then at that point, we'd have to find our RU and our RV, and we'd have to cross them and blah, blah, blah. Now, we did that once. I don't know if you remember that, because that was like a week and a half ago, and we had Thanksgiving in between, and, you know, between all the turkey and the root beers, our brains got a little bit lax, right? So I don't know if you remember, but if you go back and you look at your notes from the week before Thanksgiving, we did a parameterization of a sphere using spherical and found the RU and RV, took the cross product, and I don't know if you remember, but it was gnarly. It was really quite gnarly just to get us to that point. Then we'd have to parameterize this flux or this field, put in those parameters, which I'm not looking forward to, because now we're going to have an e to some cosine sine business, and right. So there's a lot of stuff we'd have to do there. All right. Instead, check out how fast the divergence theorem is. So we're going to start by getting the divergence of f. Okay, so divergence of f. Partial of the first one with respect to x, 0. Partial of the second one with respect to y, 0. Partial of the third one with respect to z, -1. So by the divergence theorem, we're going to be integrating -1 dv.
So I just looked at the notes you were talking about, and this is so much better.
Yeah, it is. Okay, because now you want to check this one out. Since it's just -1, well, that's the negative of just dv. What do you get when you integrate dv?
Just the volume.
You just get the volume. So this is the negative of the volume. What's the volume of the unit sphere? Well, for a sphere, it's 4/3 pi r cubed. Since r is equal to 1. Okay, there you go. There is the flux over that unit sphere of this field. Magic. Oh my God, this is awesome. I love the divergence theorem. I absolutely love it. And for those of you who are in E&M right now, you should probably see how this is terribly useful. Because how often are you looking at closed surfaces when you're dealing with like electric fields?
All the time.
All the time, right? Like almost 100% of the time. All right, well, we're gonna have to find the divergence. Are you kidding me? Of all the things that we've done with fields, divergence is probably the easiest thing to find. So it's like terribly simple, terribly simple. And if you get lucky, like in this case where you get a constant, then you don't even have to think about doing the triple integral if you can just find the volume. Okay, so here's, I mean, this is the divergence theorem. It's not really that complicated, other than the fact that it's going to bring back triple integrals. And you're going to have to try to remember, how do I set up triple integrals? That's going to be the most challenging part of this. So just be aware of that, because so far the examples I've shown you don't have terrible triple integrals. I don't know that you're going to ever run into any that are super horrible. But oh my God, it's beautiful. It's super, super nice. All right. So how do you feel about the divergence theorem?
Pretty good.
Yeah. Hopefully you're loving it in terms of the alternative. Like, go back to that one that we were looking at in homework, right? Like, I love the fact that when I got done with it, Bradley, you were like, this is not at all what they showed us, right? And yeah, it's not at all what they showed you, because they showed you the easy way. Divergence theorem, holy crap, it's so much nicer. All right, so what do you say? Let's do one more. Let's do another one here, where the surfaces give us a region that we gotta work a little bit more on. All right, so how about this guy? So same story, we're going to find the flux. And this field, we're going to go with xy minus 1/2 y squared and z. So that's going to be our F. And then this is what our surface is going to be. It consists of z equals 4 minus 3x squared minus 3y squared. And the z is going to be between 1 and 4. All right, and so this is the top. The sides are going to be given by x squared plus y squared equals 1. And then the bottom is going to be z equals 0. So this is another piecewise smooth surface. It's got 3 chunks to it. So it's got a top, it's got sides, and it's got a bottom. So the bottom, of course, z equals 0. Cool, plane. The side, what does the sides look like? What's x squared plus y squared equals 1?
Circle.
Okay, but as a surface, it's what?
Cylinder.
Okay, good. So it's a cylinder. And then what about the top? Anybody recognize what kind of surface that is?
Is that a paraboloid?
It is. It's an elliptic paraboloid, so it's a bowl. It's just upside down because of the minuses. Okay, so the top is a bowl, the side is a cylinder, and then the bottom is a plane. So what this would look like, I think I can give it a reasonably decent picture here. It's going to look kind of like that, kind of like a bullet. So basically, we took this bowl, took a cylinder, sliced down through it, and that's the solid region that we're going to set up. All right, so far so good?
Yeah.
So let's apply the divergence theorem because it's definitely closed. We're going to go with it. We've got outward orientation. All right. And let's see what this gives us. All right, so find the divergence. Well, the divergence of f, partial with respect to x of the first piece is y. Partial with respect to y of the second piece is minus y. And partial with respect to the third piece, with respect to z of the third piece is 1. So we got our divergence is 1. So divergence theorem says we're going to integrate over that region 1 dv. Now, the fact that that divergence is just a constant should make you at least start going, ooh, wait a minute, maybe we can do this faster. Because all that's going to be is then the volume of this shape. Well, unfortunately, I don't know about you guys, but I don't know the volume of that shape. Too bad. Too bad it wasn't just like a cylinder or a cone or a sphere or a hemisphere or something like that. But that elliptic paraboloid kind of screws us there. There's no good formula for volume. So we're going to have to do this the long way, but it's not that bad. All right. So in terms of how we want integration man oriented, ideas, thoughts, suggestions.
Let's do DZ first.
I love that idea. Because if we do DZ first, what are the bounds on Z?
0 for our bottom, and then the top is the yeah, Z equals that.
Yeah, the Z equals that thing. All right, yeah, it's the 4 minus 3x squared minus y squared. Definitely like that. Okay, so that's integration man standing that way. And then, of course, he's going to be able to freely walk around in the xy plane. And the region of the xy plane over which he's going, let's call it R for right now. Well, that's a circle, which definitely should make you think, let's go polar. Okay, so let's go polar. If we change this into polar, so technically we're in cylindrical, we're going to have an R dz dr d theta. The z's are actually going to go from 0 to 4 minus 3r squared. You convert that. So then what are the bounds on r and theta going to be?
0 to 2.
All right, so the r's are actually going to be from 0 to 1, because if we come back and look at the side, side was x squared plus y squared equals 1. And then the thetas, thanks Victor, are going to be from 0 to 2 pi. All right, so instead of the surface integral, we have this one single triple integral. And if we were doing surface integrals, there'd be 3 of them again. We'd have to do one for the top, we'd have to do one for the sides, and we'd have to do one for the bottom. Now, some of them are pretty easy. Like the bottom, since that's z equals 0, I know what vector I want to use. I'm going to use the vector 0, 0, minus 1. That's my outwardly pointing normal vector. So that's pretty easy to dot with our field there and get our value. The side, well, that one, again, the parameterization is pretty easy because it's just a cylinder. And the top, since it's a function, I don't know if you remember, but there is a way of finding those normal vectors pretty easily for functions. And those were where you did either the negative partial with respect to x, negative partial with respect to y, comma 1, or the positive partials with x and y, comma negative 1. Again, go back in your notes and you'll see those. This one, since I want it to be pointing outward, which would be upward, I'd need my z component to be +1. So I could use the negative partial with respect to x, negative partial with respect to y, comma 1. That's pretty easy to get from this, right? But the point is I'd have to do 3 of them. I'd have to do 3 different surface integrals as opposed to the one triple integral. And in fact, let's go ahead and get this guy real quick. Because when we integrate with respect to z, we get a z, r times z would be 4r minus 3r cubed. So that's going to give me a 2r squared minus 3r to the 4th over 4. So 2 minus 3/4 is 5/4 times 2 pi, I believe, is going to be 5 pi over 2. I'm going to put a question mark on that because I really don't trust that, but yeah, I think. All right, but there you go. There is the flux over the surface. So now that you've seen how fast and easy it is, let's talk a little bit about what that number means. Kind of relate that back again. So flux. Remember, it's a measure of flow through the surface. And so we got a positive number here. So what does that mean?
There's more going into the surface than outward.
Okay, so what do you guys
Wait,
think? More
no,
going.
opposite. It's going out.
Okay, so it means that there's more going in the direction of the normal vector than opposite it. And so we've got our normal vectors pointing outward. So this positive means that there's more flow going out than coming in. So, all right, good, Victor. You were just anticipating what I was about to say. So that definitely does mean that there is a source on the inside. So if we were talking about whatever kind of field, right? And I don't care if it's electric field, magnetic field, gravitational field, whatever. This would mean that inside this surface, somewhere in there, is a source, something that's producing whatever stuff is that's flowing. Okay, so there's a source inside. If you go back and you look at the example that I did before this one with the unit sphere, we got a value of negative, I think it was negative 4/3 pi. So think about what that meant for that one. That meant more was coming in than going out. So what does that mean if you've got a negative? What's on the inside there? Do you remember what the opposite is of a source?
Source free.
Source free means that you get a divergence of 0, so you'd always get 0. So it's not source free, but the opposite of a source is a sink. So if you got a negative, that means there's a sink somewhere inside. When it comes to electricity, just think source and sink, positive versus negative, right? If you got a positive charge on the inside versus a negative charge on the inside, it either repels or attracts. If it's like fluids, a source is what it sounds like. There's something pumping water in. If it's a sink, there's something removing water. That's why it actually gets the name source and sink is from fluids. But anyway, so that's what these numbers are actually meaning. And if you get 0, it just means everything's balanced. There's no flow in or out. If we have a source-free field, the divergence of F is always 0, right? And so for this is one of the reasons why it's good to check if you've got a source-free field, why we actually care about those, is check this out. For a source-free field, so let's see, if F is source-free, what that tells us that the flux over any closed surface is equal to 0. Right? Because by the divergence theorem, we get that this is equal to the integral, triple integral of the divergence of F. But by definition, source free means divergence of F is 0. And therefore, your double integral is equal to 0. All right, so source free is kind of a big deal. It's very similar to conservative in terms of its usefulness, but in this case, the source free is useful when it comes to talking about flux. All right, so what do you guys think? You like divergence theorem?
It's pretty cool.
It's pretty cool, and it's definitely really, really useful in lots of situations when you got closed surfaces. So now you can go back and see why for that one homework problem and perhaps others, why divergence theorem might be kind of useful. Okay, so I think as far as an audible went, that didn't go terribly. I might have some more things to talk about divergence theorem. I have to just double check, make sure that there isn't anything special that I kind of forgot to mention. If so, we'll talk about that next time. But just to remind you, on Wednesday, we're going to start with a quiz, like we always do. That quiz is going to be on surface integrals. So it's going to be on 4.6? Oh, let me check that real quick. Oh, not even for 6.6. All right, so it's just going to be on surface integrals. So it's going to be things like parameterizing curves, calculating surface integrals, calculating flux integrals, and so on. I don't think any of it will have divergence theorem applicable, but if it does and you want to use it, feel free. All right, but the quiz is just going to be over 6.6. I want to make sure that you guys have surface integrals down because they're kind of important in terms of these last couple sections. All right, so we'll do that first. Then I'll wrap up any last little bits about the divergence theorem, and then we'll talk about Stokes' theorem and just a little preview for you what Stokes' theorem does. It relates surface integrals to line integrals. So once we get that in, we've kind of got everything, right? Green's theorem relates line integrals to double integrals. Divergence theorem, surface integrals to triple integrals. Stokes' theorem is going to be line integrals and surface integrals. So anyway. All right, so any other last questions before I stop the recording?
Did you say the quiz was on Wednesday, or did I mishear that?
It is on Wednesday. Yep.
Okay.
Which is different than our normal. It is on the syllabus as well, but yeah, it's going to be on Wednesday. That way I can actually get them graded and we can talk about it on Friday, since Friday is our last day of class.
Gotcha. Okay.
All right. Anything else before I hit stop on the record? All right. Well, with that, have an awesome couple of days.